All right, welcome to another thrilling installment of Miss Andrews' Advanced Algebra Notes. So, we were working with our parent graph toolkit today. We did a group project with this, and each group did a different parent graph and investigated that. So we're going to go through here and sum them all up for those who were not here. So the linear is a y equals x for the parent equation. It's the most basic line you're going to get. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, so on and so forth. Negative 1, negative 2, negative 3, negative 4. X and y are equal all along that line. So that is our parent graph. The point slope equation of this is y equals a times x minus h plus k. That's also called the point slope equation, or the general equation. And in that particular one, hk is, so our locator point, hk can be anything, any point on that line. A on a linear equation happens to be the slope. So this is why this is referred to the point slope equation. So a point on the graph and the slope. Anything you plug in for hk on that line is going to make that valid equation. Our domain, negative infinity to positive infinity, are all real numbers. Same thing for the range. And this has no asymptotes. Our quadratic we worked on with the Parabola lab the other day. That is y equals x squared. That one has a vertex of 0, 0, goes out 1 and up 1, out 1 from there and up 3. And when you are graphing a parabola, that is my expectation of the points that you show. So you very clearly show the points graphed as 0, 0, 1, 1, and 2, 4. That's if it's the parent graph. Obviously, if you move it, you're going to change where that placement is. The general equation, the vertex form, is y equals a x minus h squared plus k. And hk is equal to the xy coordinate of the vertex. So what we're going to find with all of these graphs is that as we move this around, as xk changes, this is our locator point. This is the easiest point to move it over and up or down and around anywhere. But that's the place we're going to start because that's the easiest way to do it rather than using a table every time. The domain here, negative infinity to positive infinity. The range depends on what h is. Just kidding, what k is. I'm going to put this in general as from k to infinity. But that should also indicate that if the parabola gets flipped over, this is going to swap from negative infinity up to k. So you need to make sure to pay attention to that. And there are no asymptotes on this one either. The cubic equation is y equals x to the third. And what that looks like, you have the point 0, 0. 1 cubed is 1. Negative 1 cubed is negative 1. Those 3 points are the ones you need to show. What happens there, because this is not just a little straight line, is as you go out, 2 cubed is 8. So this jumps up quite a bit. And negative 2 cubed is negative 8. So that drops down quite a bit. So as you get further positive and further negative, that goes faster. So we have kind of a little swoop there. And this point in the center, that's our HK point. So our general equation, y equals a times x minus h cubed plus k. And hopefully you're starting to see a little bit of the pattern. So hk, this can be referred to as many different things. Some people call it where it flattens out a little bit. One of my classes came up with the swoopy point. So it's kind of however you describe it that works for you. Just make sure you understand that the center point and its two next points need to be very clear on your graph. And as you're looking at this, the domain from left to right, there's nothing that we cannot put in for x. So even though it looks like this starts to go straight down and that starts to go straight up, just go up very, very quickly. So x will continue to go out in both directions, and range as well is going to be negative infinity to positive infinity, and we do not have any asymptotes either. Something that we're looking for in asymptotes is what kind of values you can't have for that. So like, or what kind of values that will be approached but never reached. So we come to that in our rational parent equation, which is y equals 1 over x. What that one looks like, because x cannot be 0 because you can't divide by 0, then I have a vertical asymptote at x equals 0. And you always want to note that with a dashed line. And because I can't put in 0 for x, that means there's nothing that I can put in for x that's going to give me 0 for y either. So I'm going to have a dashed line at y equals 0. So here's what happens. If I go out to 1, 1 over 1 is 1. 1 over 2 is 1/2. 1 over 3 is 1/3. 1 over 4 is 1/4. So what's happening is I'm getting closer and closer and closer to that y-axis, but I'm never going to get to it. At -1, 1 over -1 is -1. -2 is 1/2. And the same thing is happening over on this side, that it's going to get closer and closer to that y-axis. What happens in between -1 and 1, you have to look at the values of x that are in between there. So if I look at where x equals 1/2, you can't see that. Where x equals 1/2, 1 divided by 1/2, if I split 1 into halves, I have 2 halves. So this is going to be a value of 2. And if I go to 1/3, it's going to be a value of 3. And 1/4 is going to be 4. And if I have 1/100th, which is teeny, teeny, tiny, close to that line, that's going to be way up here at y equals 100. So that's going to approach this asymptote infinitely going up. And the same thing happens down here as well. So when you graph a hyperbola, the important things that you need to graph are the asymptotes first, because this point in the middle where those asymptotes cross, that is your HK point. That's your locator point. And then when you draw these two, the points that I need to see are really this one and this one. And then you need to draw the rest of that curve in. But the points that I want specifically are these two. So the HK point is where the asymptotes intersect. So because x cannot be 0, I have an asymptote where x equals 0. And because I can never get a y out of this, I have an asymptote at y equals 0. So I have an asymptote here and here. My domain on this is going to be related to hk, so negative infinity up to what h is. In this case, it's 0, not including h, and then from h out to positive infinity. Down here, same thing, only it's going to be k. That is what's also called a hyperbola. And then the general equation, which I almost forgot, is a times 1 over x minus h plus k. You can always also write that as a over x minus h, just depends on your preference. Radical equation, y equals the square root of x. Square root is also referred to as a radical, so that's why we're calling it that. General equation, y equals a times the square root of x minus h. Make sure when you write this, you're very, very clear that that square root sign ends after the h, and then you have plus k. What this one looks like, because it's the inverse of a parabola, is basically a sideways parabola. So the square root of 0 is 0, square root of 1 is 1, square root of 2 is not a whole number, 3 not a whole number, square root of 4 is 2. You'd be out a ways, as the square root of 9 is 3. So you're going to see that pattern, that up 1 over 1, up 1 over 3, in the same way that we do with the parabola, only it's turned sideways. Now, we can also write this down here as a dashed line because technically the square root of 1 is also negative 1, because negative 1 times negative 1 equals positive 1. However, that is not a function because you can only have one y value per x value in an actual function. So this doesn't pass what's called the vertical line test. So this part right here with these 3 points are the ones that I want to see. So I want to see that upper part. Whether or not you do the dashed part down there is up to you. So HK is basically the quote-unquote vertex of our sideways parabola. So this domain, this particular one, goes from 0 to infinity. So here from infinity, that's also h included out to infinity. The range is going to be from k included out to infinity. It'll go up slowly, but it will keep going up, and there are no asymptotes. The parent graph equation of absolute value. These 2 lines outside of x are the absolute value brackets. So the general equation, y equals a, x minus h plus k. So when I graph that, anything coming out of the absolute value is going to give me a positive number, because absolute value is the distance from 0. So if I have negative 1, negative 2, negative 3, they're still 1, 2, and 3 away from 0, just on the other side. So on the positive side, the absolute value of 0 is 0, 1 is 1, 2 is 2, 3 is 3, so on and so forth. So this looks a lot like a linear one, but when I go to negative 1, the absolute value of negative 1 is positive 1, and negative 2 is positive 2, negative 3 is positive 3. So this turns around in a perfect V. So HK in this one is 0, 0. I'll go ahead and label that on this one as well. So that is the point, or that's basically the vertex. The domain is all real numbers because you can put anything in for x, so negative infinity to positive infinity. The range, however, is wherever k starts. So I'm going to go from k included to infinity. The only thing you need to watch for with that general part of range is that if a is negative and that flips this so it's pointing down, because if the negative is outside of those brackets, that makes everything negative, then this would be negative infinity up to k included. And we have no asymptotes on this one as well. The final one on here is the cube root function. So the parent equation is y equals, it looks like a square root, but there's a little 3 here. And then the general equation, y equals a, cube root x minus h and then plus k. Hopefully you're kind of seeing that pattern. So I'm looking at what numbers multiplied by itself 3 times is going to give me that number in x. So I'm going to start with what my whole numbers would be. So 0 multiplied by itself 3 times is going to give me 0. The next number that's going to have a perfect cube root is going to be 1, because 1 times 1 times 1 is just 1. And -1 times -1 times -1 is a -1. The next one out is going to be out at 8, because 2 cubed, 2 times 2 times 2, is 8. So I'm going to put this out here, and then -2 times -2 times -2 is -8. So this one, hopefully you're noticing, looks an awful lot like the cubic one, but it's turned on its side, very much like the parabola and the square root were turned on their sides from one to the next. So this point right here, that's your HK. The points that I expect you to graph when you are graphing one of these for a test or a quiz are those right there. You want to make sure that your arrows are pointing in the right direction as well. So your locator point, HK, is the center point, the turning point, the swoopy point as it came up in the other class. And I think we decided that was the spelling for it. So however you want to think about that one, it kind of flattens out there. It's whatever it is to you. Domain and range are both -infinity to +infinity. And there are no asymptotes with this as well. So I want to do a few examples. I'm not going to do all of these. Excuse me. So when I look at this, these are all the square root of x. So these are all the absolute value. This is the parent function of that one. So if I move it left 2, that's going to be right there, going straight out 1 to 1. And we know that to move it left to right, we have to change h. So that's going to be x plus 2, because remember that inside of the grouping symbols, when we're dealing with h, that makes it move left or right. So x plus 2 makes it move left, x minus 2 makes it move 2 to the right. So if I want to move it right 1, this is going to be x minus 1. The vertical compression of 1/4, so that means I'm going to have 1/4 x, because that's all I'm doing to it. What that means is that instead of going out 1 and up 1 in both directions, I'm going to go out 1 and up 4. So this is going to be a very, nope, just kidding. Because it's 1/4, it will be wider. That would be if it was 4. So it's going to go out 4, up 1. My deepest apologies for that error. So this is going to be much wider than a typical one. A vertical stretch by a factor of 3. So that would be 3 absolute value of x. So that means I'm going to go, starting at my vertex, out 1, up 3, instead of out 1, up 1. So that's going to be a much skinnier one. Whoops. Yeah, I won't worry about that. We're not going to worry about the horizontal stretch or shrink. That is a pre-calculus concept that we do not need to mess with. If we move it up 3, that's going to be the absolute value of x plus 3, because k is what moves it up and down. So I'm going to take my vertex, take it up to 3. Down 4, absolute value of x minus 4. Still going to be pointing up. Going out 1 and up 1, that was not super duper precise, but you get the point. reflection across the x-axis. So this is the x-axis. So what that means is we are taking our, I'm going to put this in really lightly, taking our parent graph and flipping it so that it reflects over the x-axis. So anytime we flip over the x-axis, that means our a is negative. It's a negative absolute value of x. So whatever comes out of here is positive, but then that negative makes it negative, so the whole thing is pointing down. Reflection across the y-axis is going to look exactly the same with the absolute value. So we're not going to worry about that one too much either. So those are the different transformations. The worksheet you have has several different transformations at a time. And I want to show you the hyperbola one because that's the one that people struggle the most with. So on the worksheet 1-6, on part C, I'm going to zoom in on that because you need to be able to do these without calculators, because you don't want to calculate all the values for x and get your y out, because that's just a lot of work you don't have to do. So for this one, my a is 1, so I'm not doing any kind of shrink or narrowing or widening of the hyperbola. But I know my hk is -2, because remember with h it's always the opposite of what you would think it would be, and then -3. So what that means is I'm going to put a vertical asymptote at -2. Then I'm going to put a horizontal asymptote at -3. And then I want to look back really fast at our other one. That we had. Sorry. Badly done. So this one had these 2 points, 1, 1, and -1, 1. So those were exactly diagonally 1 away from our HK. And that's really what we need to notice. We don't need to try to figure out what the value of y would be at x equals -1 and x equals 0, because that's just more time than we need to spend. So we're converting these not by doing this mathematically, but by doing it more visually. So the 2 points we're going to have are here and here. And we know that as we get closer, we see these points get closer and closer on each side. So this is going to come right up against the horizontal asymptote and then go all the way down close to the vertical asymptote and never touch it. And the same thing's going to happen over here. It's going to come down and swoop out. And those arrows are indicating that these are coming so close up to the asymptote, and I should change that just a tad. But they, once again, are never going to touch it. So that's how I would expect you to graph that parabola, not by plugging in the points, but by, hyperbola, but by using the patterns that are in the parent graph. So that is 1-6. We're probably going to go over some of those in class, but I wanted to have this out there because we did not have time to go over this very thoroughly in class. Have a lovely day.